Alright, this section, section 3.1, the title is Algebraic Linear Equations. Essentially here we're just going to be looking at maybe some more examples of solving some more equations, just solving for x or whatever the variable is. But we're also going to throw in some word problems, some story problems, and kind of see how, we might some examples of taking a word problem and solving it with an equation, but with it being a word problem, we're going to have to first come up with the equation and come up with what the variable is going to represent and how that variable gets included in the equation so that we can solve for it. So let's dive right into some examples. Again, nothing any more advanced really from section 3.0. Remember, we have an overall kind of hierarchy, like a step-by-step procedure of what you're going to be looking to do first, and then as you go along, like what kinds of things you're looking to do in what order. This particular example, the first thing I think we should do is clear the parentheses. So I don't think we did an example quite like this in the 3.0 notes, where what are we distributing here? It looks like we're just distributing a negative sign, which is true enough. You could really think of it as distributing a -1. There's technically an invisible 1, so -1 that's being multiplied to both the 2 and the x. So, me personally, I just think of it as we're distributing the negative sign. So we're going to clear the parentheses, so the 2x just drops down, and then this negative gets distributed to the 2, and the negative also gets distributed to the positive x. So that's what this left side becomes. And the right side, of course, is -12, so everything else kind of drops down. Now, looking fresh at what we have now, what would be the next thing you think we should do? How should we proceed? Remember, you might have heard me say last section, or even before that, in weeks and months past, that you don't have to do a certain something next, but what I would have you do next is notice that there is like terms. There's a 2x and there's a -x or -1x, and they're already on the same side. So there's like terms that are already on the same side. So that's the next thing that I think we should do. Just combine them. 2x minus 1x just becomes 1x, and this -2 term just drops down, and then of course the equal sign and the right side of -12. Okay, now looking fresh at this, isn't it now time in the process? Like once you've cleared parentheses and once you've taken care of any like terms that could be combined that were already on the left side together or already on the right side together, what happens after that? Well, what happens after that is you move on to, well, do you have an x variable on both sides? Because the next thing you should probably want to do is make sure you only have a variable on one side. In this example, that's already done. Like, we don't have to do anything about that because we only have an x now over here. Like, there was no x over here as well. So after that, once you get the x only on one side, now you want to get that all by itself. In other words, we don't want this left side to say x minus 2. We just want it to say x. So this -2 has to be canceled out. We got to move it out of there so that x can be all by itself. And of course we do that by doing the opposite, adding 2 to both sides, and that leaves x all by itself like we want for the end. And then -12 plus 2 is -10. So that's the solution. X equals -10. Another example, similar, if you want to pause and try this yourself, but I'm just going to dive right in. So last chance to pause. Similar to the one we just did, we're going to distribute this negative sign, which is essentially a negative 1. So it's like negative, if I thought of it as a negative 1, negative 1 times 2x is negative 2x, and then negative 1 times 1 is negative 1. And then you would notice that these like terms can just combine because they're on the same side. So they just become 1x, or x. And then all you got to do from here is cancel out this minus 1 by adding it, and you get a final answer of negative 5. Okay? So again, nothing too different from last section. I mean, what kind of plot twist is this? It's not much of one. I mean, the rules remain, and the basic steps remain, that you want to first clear any parentheses that might be around at first. Do not be tripped up by the fact that it's a 0.6. Nothing too different. You know, it's not like it's nothing you can't deal with. So we're just going to distribute 0.6 the same as if we were going to distribute just 6. And over here, this other bubble, we're going to distribute 0.2 just like we would distribute any other number. So 0.6 times 1, 0.6 times negative x. Same over here, like 0.2 times x, and then 0.2 times negative 5. Remember, use a calculator if you need to. But this is what you get when you clear the parentheses. From there, you're going to want to notice that there's some like terms already on this side together, like this 0.6 and this minus 1, and that is a minus 1. The sign is included with the term. So 0.6 minus 1, and then as well as the negative 0.6x plus 0.2x. So those two pairs of terms can just combine as is. So 0.6 minus 1 is this, and then negative 0.6x plus 0.2x is negative 0.4x. Use a calculator to get those answers if you have to. But now we're here, and once again, I don't think we need to move any x's to the other side. We only have this x right here, so we just got to like get rid of this term and then get rid of the negative 0.4 times x. So what's the opposite of multiplication? Division. And probably using your calculator, I bet I used my calculator at least once or twice on this problem to get the final answer of negative 26. Pause if you need more time to copy all that down and whatever. But next one, number 4. So this will be the last, just straight up equation given that you need to solve for x. This has a little bit of a curveball, I guess, with fractions, or maybe, yeah, this is just a fraction. I guess you could refer to this as a mixed number. 28 and a fourth, 91 and a fourth. At least a couple different ways to attack this and get this rolling with your next step. I think what I would recommend for something like this is noticing that these fractions are kind of nice fractions. Like they're some of the nicest fractions you could possibly hope for. 1/2, 1/4. So rather than maybe keeping them as mixed numbers or even turning these into improper fractions, I think, what I did here is just write it as a decimal. 28 and a fourth is equivalent to 28.25, and 1/2 is equivalent to 0.5 as a decimal, and over here same. So you don't have to write it like this, but I think it helps, especially if these are really nice decimals from certain fractions, right? And now you just kind of get on with the business of what? Eventually having x only once and getting it all alone on one side. I have a couple of x's, but they're already on the same side. So just combine them. Combine them as is. This is 1x. This is 0.5x. So together they make 1.5x. And then this term just drops down. Yeah, there was no parentheses to clear or anything like that. What's next? I mean, I guess just move on to the business of getting this x all by itself. So first we have to undo this adding of 28.25. So we do that to both sides to get rid of that guy. And now that leaves us with 1.5x on the left. And on the right, you know, maybe using your calculator, I wouldn't be surprised if I busted out my calculator to see that this is 63. And then the last thing we have to do is cancel out this times 1.5 to leave x all by itself. But, you know, so we divide both sides by 1.5. And then we, you know, 42. Again, would not be weird at all for you to need your calculator to do 63 divided by 1.5, but that is 42. Alright, again, pause the video to get that finished copied down if needed, but let's move on to some very fun word problems. How many are there going to be here in the notes? We have that one, we have that one, we have a few. So we have a few story problems to do. And again, like I said at the beginning of the video, we're going to see how to do this with an equation. We have to come up with the equation ourselves, including the variable and how that fits into the equation along with all the other numbers and stuff. I do want to point out really quick that I'm not going to pretend that there's not other ways to do this, other ways that you might find a little more easy to wrap your brain around, like the method of just guessing and checking, you know. So here we have, like, Josh has $5.85 in dimes and quarters. He has some dimes and some quarters, and together it totals $5.85. And this other little detail is that he has 6 more dimes than he has quarters. And the problem is basically like figure out what the number of dimes and quarters are, you know, to satisfy this criteria, you know. You could totally guess and check. I'm not going to pretend that that's not a valid method, but in the same breath, I'm going to tell you that guessing and checking will work like plenty of times, but there's going to be story problems where guessing and checking is just not going to cut it. And for now, just trust me on that. We don't need to go into the reasons why or an example of what I'm talking about, but this problem we could totally guess and check. But we're going to come up with an equation to do this. And as a matter of fact, because my one equation, you know, let me give you a little bit of a peek. So one of the equations I could write, or like the main equation, is going to be about how this all equals the $5.85. Because at first we don't know how many dimes there are, and we don't know how many quarters there are. That's literally what we're supposed to be finding out. So oftentimes in a story problem, whatever they want you to come up with for the final answer, that's exactly what your variables are going to be taking the place of temporarily. So we're going to just use D for the number of dimes, the unknown number of dimes, and Q for now as the unknown number of quarters. So the way money works with dimes and quarters is this. Oh, sorry. So to equal the $5.85, you're going to have to take the number of dimes, whatever it is. For right now, it's just D, you know, D dimes, and literally multiply that number, whatever it ends up, whatever it's supposed to be, times 0.10, which is like, 10 cents. And then what's going to be here? This is basically how much money we're going to have in dimes, which would make this represent the amount of money that we have in quarters, because you're going to take the number of quarters, whatever it's supposed to be, and then multiply by 0.25. So then add these up and you get that. So there's an equation, right? Like we have this equation just coming right from the reading, from the story problem. But here's essentially our dilemma. We now want to solve for D and Q eventually, right? Find the number of dimes and quarters. But when there's two variables, you can't really solve and get like a really clear final answer. Like we can't just like get D by itself and have like a clear answer. We can't just get Q by itself and end up with like a super final clear answer. So there's two variables. We can only really solve equations the way we want to when there's only one variable. So here's what we have to do. This other piece of information, the fact that there's 6 more dimes than quarters, if we're being thorough here, like very all the way writing everything out thorough, there's another equation that can be written with D and Q, and it's this one. Looks a little bit simpler, but it's still an equation. D literally equals Q plus 6, right? 6 more dimes than there are quarters. So whatever the number of dimes is, we know it's literally equal to the number of quarters plus 6. That's the same as dimes. So we have an entirely other second equation. And then what happens next is that allows us to make a replacement, like a substitution, like a switch. Because instead of just having the D variable, can't we just write Q plus 6 instead, because they're the same? Wouldn't they be now interchangeable? Like they're literally the same, D and Q plus 6. So we make that switch. It's called like the substitution method. And once we do that, now we have an equation we can solve. Can we not now solve this for Q? Because now we only have Q in our equation? Of course. So what do we do first? Don't we clear the parentheses by doing the distributive property? So 0.10 times Q, and then 0.10 times 6, which is 0.60, or 0.6. And then everything else just drops down. And now what we see is that we have like terms already on the same side, so they should just combine, right? Like we know these steps by now, right? Hopefully. And so we have this, and now we just keep on. Remember, the end game is ending up with whatever variable all by itself. So the rest of this, I hope we don't need to write down. I mean, I'm out of room. You might not be out of room, but what's going to happen next? Aren't we just going to subtract 0.60 over to the other side and then divide both sides by 0.35? And if we do that, we're eventually just going to get Q equals 15. So what does that mean? What does Q equals 15? That means what as a solution? I'm not trying to trick you, just means there's 15 quarters. So remember, Q is the number of quarters, so this means we had 15 quarters. Well, we also need the number of dimes. Wasn't that easy to figure out if we know that there was 6 more dimes than quarters, which is kind of represented by this equation? So if we had 6 more dimes, that means we had 21 dimes. And you can double check to see if this makes sense. 15 quarters and 21 dimes. If that does in fact come out to be $5.85, but it does. At least I think it does. So that's that example. The next example, fairly similar. We got $68 selling Snickers and Milky Way candy bars, maybe a fundraiser of some kind. Wendy charged $1.75 for each Milky Way and $2 for each Snickers. How many of each did she sell if she sold 36 candy bars total? So once again, I don't think I literally wrote down like I did here what our variable, like how many variables do we have? Is there only one unknown or is there two unknowns? Isn't there two unknowns? Because we got to figure out how many Milky Ways there was and how many Snickers there was. We know the total's 36. So we're going to have two variables. And I think I'm going to use M for the unknown number of Milky Ways and maybe S for the unknown number of Snickers, okay? And once again, you think we could probably guess and check for this one? You know, do we need to write out an equation with variables and then solve the equation to figure out this answer? No, you could totally guess and check on this one. But trust me, you need these skills. So, using M and S, what would be our equation that would end up, representing how we total up $68, right? What do we do? Using the number of Milky Ways, which is unknown right now, we just got to say M, and the number of Snickers, which we don't know right now, we just got to say that it's S. How can we stick those in an equation where it basically calculates how we end up equaling $68? Wouldn't that be accurate? $1.75 times the number of Milky Ways, $2 times the number of Snickers, and when you add those up, that should be the 68. But again, can't really solve this the way we want to solve it and get like a final answer when there's two variables. So one of these variables is going to need to be replaced with something equivalent, but that it uses the other variable, so that we only have one variable to use. So we're going to have like another equation, and apparently that's got to be using the fact that there's 36 candy bars total. And so that's going to be the equation. Literally, M, whatever it is, plus S, whatever that is, needs to equal 36. So I think the difference, or the slightly more advanced thing about this problem versus this problem is that this one was already saying like, hey, you know what? D is literally equal to Q plus 6, so we could just make a straight up trade replacement. But wouldn't we need this equation over here to say that M equals something with S, or S equals, like we need one of these variables by itself. So you got to do this quick step first, like maybe move the S to the other side by subtracting it. That's not very nice. I'm writing with my mouse. So now we know that M equals 36 minus S, which means we can replace this M with 36 minus S because they're equivalent to each other. So you could just say that. And again, the reason that was such a good move is that now this equation only has the variable S. And so we can solve for S. We distribute, of course. Gonna want to clear that bubble first, clear the parentheses. And so 1.75 times 36, bam. 1.75 times negative S, bam. Everything else drops down. Look, these two terms combined together, they're already on the same side. The negative 1.75S and the 2 S. The 63 just drops down. And then, yada, yada, yada. I don't think I need to drag our feet through these last few steps. Once we finish getting S all by itself, apparently, S equals 20. What does that solution mean? What does S equals 20 mean? It means there was 20 Snickers bars. So 20 of the 36 candy bars sold were Snickers. So doesn't that mean that there was 16 Milky Ways? Yep. Last example. Similar, but some plot twists and some extra juicy, things to kind of deal with. Let's see. A belt costs $30 less than a pair of jeans. The ratio of the cost of the jeans to the cost of a shirt is 2 to 1. I don't know if you understand what that means. I guess we'll get to that in a minute. So what do we have so far? A belt costs $30 less than whatever a pair of jeans costs. So we're not saying the belt costs $30. We're saying whatever the jeans cost, the belt is $30 less than that. And then the ratio of the cost of the jeans to the cost of a shirt is 2 to 1. Oh, maybe I'll get to that right now. That just means that the jeans are going to cost twice as much as a shirt. If the total cost of the three items is $75, find the cost of the jeans. So all we need to figure out is the cost of the jeans. But that doesn't really mean that there's not, at the beginning, 3 unknowns. We don't know the cost of the jeans. We also don't know the cost of the belt, nor do we know the cost of the shirt. So we can at least get this going, where whatever the jeans cost plus whatever the belt costs plus whatever the shirt costs, we know that it's all going to add up to $75. Okay? But look, we can't just say, oh, J plus B plus S. We can't solve an equation where there's like 3 different variables. So we're going to have to basically need to describe 2 of these in terms of the third one. And we're going to go with J. So basically jeans, that's easy. The cost of jeans is literally J. So how can we describe the cost of the belt using J, which is the cost of the jeans? What do we know about the belt? We know that the belt costs $30 less than whatever the jeans cost. So how could we say that using, J? Like that. This is essentially the cost of the belt, the cost of the jeans minus 30, is it not? And then the shirt, what did we say? That this ratio of 2 to 1 means that the jeans cost twice as much. So how could you represent the cost of a shirt using J, which is the cost of jeans? Well, like that. Okay? And then now that we have an equation that only has one variable to worry about, we can solve for that. So, some quick details, some quick comments. I included these parentheses, but now that we don't really need these parentheses. They're not really doing much, If you wanted to clear these parentheses by distributing a plus sign, knock yourself out, but that's not going to do anything. These parentheses aren't really needed, So we can just move on to doing J plus essentially 1/2 J. So when we combine all those together, 1J plus 1J plus half J, because you could write this very easily, J over 2, you could think of that as 1/2 times j, like 1/2 j. So we end up with that. Combining all those like terms together, and then the minus 30 drops down, and then from here we just got to what? Add 30 to the other side, and then divide both sides by 2.5 to eventually end up with j equals 42, meaning that the jeans cost $42. So if the problem would have asked for all of it, then you could have just said the belt cost $12 and the shirt, that would make the shirt, what, $21 if you needed to include that in your final answer. But yep, so there's some examples of story problems that probably could have been done easily enough just using guessing and checking, but it's a matter of coming up with 2 or 3 variables, at least at first, writing out an equation or 2, or technically 3. This technically came from b equals j minus 30, and this came from s equals j over 2, or I guess you could have originally wrote it as j equals 2 times s, and then just divided the 2 over there to... So multiple equations kind of coming together to make an equation that's actually solvable with only one variable. Alright, so that does it for section 3.1.